Let us start this solved example of a curved beam. For the simple curved beam shown below, determine an expression for the vertical displacement under an applied load F. So as you can see, the beam is curved and a force F is applied at the top. So we take a general point which has an angle of theta and the force applied is F and the radius of the curved beam is R. From the Castigliano's theorem, we have y equals 1 over EI integral m del dabba mo dabba f dx. That is the basic equation for the beam bending of beam bending. Okay. So from 0 to 5, you can write, if you look at the previous diagram, we take a general point at an angle of theta. So the moment after the theta is Fr sine theta. As you know, if you divide it for the component, the moment acting on the point where the angle of theta lies is Fr sine theta. And if you integrate this moment with respect to force F, you will get dabba mo dabba F, which is equals to R sine theta. Thus y equals 1 over EI integral from 0 to 5 R sine theta into R sine theta into R d theta. Since dx is equals to R d theta for a small angle, you can take dx which is equals to R d theta. And moment is Fr sine theta into a dabba mo dabba F, which is equals to R sine theta. So when you simplify this equation, you get y which is equals to Fr cube divided by EI integral 0 to 5 sine squared theta into d theta. So now you note that sine squared theta, which will be expressed as half 1 minus cos 2 theta. Therefore y which will be equal to Fr cube divided by EI integral from 0 to 5 half minus cos 2 theta divided by 2 into d theta. So integrating this problem, you will get y which is equals to Fr cube divided by EI 5 divided by 2 minus sine 2 theta divided by 4. Since integral of cos 2 theta is sine 2 theta divided by 2, so you get sine 2 theta divided by 2 into half, which is sine 2 theta divided by 4. And y equals Fr cube divided by EI 5 divided by 2 minus 0 plus 0 minus 0. Finally, y which will be equal to 5 Fr cube divided by 2 EI. So now we'll consider sample quiz, which is a curved beam. So from the earlier expression, we can solve this equation, this problem. A simple curved beam of radius r, which is equals to 600 millimeter, is made from steel bar whose Young's modulus of elasticity is 209 gigapascal. The beam is subjected to a vertical load at its free end of magnitude F, which is equals to 50 Newton, and its cross-sectional dimensions are shown. Calculate the vertical displacement at the free end. Determine a general expression for the stiffness of the spring of this form. So now if you look at this, they have given the cross-sectional details as well as they have given the radius and the force and the Young's modulus. So we just, if you look at the previous equation, y which is equal, you can use this expression y equals phi fr cube divided by 2ei. So you can use this result in order to calculate the displacement. So you can get the moment of inertia as bd cube divided by 12, which is equals to 0.025 into 0.006 to the power of 3 divided by 12, and you will get the answer of 4.5 into 10 to the power of minus 10. Y, which is equals to the previous equation phi fr cube divided by 2ei, which will be equal to 5 into 15, that is the force, 0.6 is the radius, which is the cube, divided by 2e and I. So the moment of inertia is 4.5 into 10 to the power of minus 10, and the Young's modulus is 209 into 10 to the power of 9. So it will give the result as 0.054 meters or 54 millimeters. So y, which is now, that is the, if you look at the previous slide, you should see that y, which is equals to phi fr cube divided by 2ei. You can use this expression to determine the general expression for stiffness of the spring. Okay, so y, which is equals to 5 into fr cube divided by 2ei for a linear spring F equals ky, which is equals to F equals k into 5 fr cube divided by 2ei. So you cancel out, so you get the expression for the stiffness is k, which is equals to 2ei divided by r cube into 5. So we will consider this solved example of a David beam. For the David beam shown below, determine an expression for the horizontal displacement at its free end in the direction of applied load W. So you can see this is a fairly long David beam which has a length L, and at the end it has a radius of R, and which has a quadrant. So you can see the length L, and you have taken a general point X from the start point X, and you have to consider from X to Y and Y to Z, since there are two portions of the beam. So as you know, the strain energy function is scalar, and therefore separate strain energy quantities can be developed and added together before proceeding to use Castigliano's theorem. So we will take the displacement delta W will be horizontal displacement under the load W. So from the Castigliano's theorem for beam bending, you can write as 1 over 1 divided by EI integral m into da by m over da by w dx. From x to y, m equals wr and the da by m divided by da by w, which is equals to r. From z to y, which is m, which is equals to wr sine theta, which is the moment which acts from y to z, and da by m divided by da by w is r sine theta. So the moment will take from x to y, which is a constant moment, which is w into r, and y to z is w into r sine theta, because the moment varies along the curved beam. So thus we, after integrating, you can get da by w, which is equals to 1 over ei integral 0 to L m into da by m over da by w dx. This is from x to y, and 1 over 1 divided by ei integral 0 to 5 divided by 2 m into da by m over da by w r d theta. That is z to y, from which we will get this expression, which is delta w, which will be equal to 1 over ei wr into r dx, 1 over ei 5 divided by 2 to 0 wr sin theta into r sin theta r d theta. Delta w, which will be equal to 1 divided by ei integral 0 to L wr squared into dx plus wr cube divided by ei 5 divided by 2 into 0 sine squared theta into d theta. So you can write sine squared theta, which will be expressed as half 1 minus cos 2 theta. So therefore you can get after integrating, you will get da by w, which will be equal to wr cube divided by ei x, which is L to 0, plus wr cube divided by ei 5 divided by 2 minus sine 2 theta divided by 4. This is the expression you will get after solving the above equation, which is equals to 1 divided by ei integral 0 to L wr squared into dx plus wr cube divided by ei 5 divided by 2 divided by 0 half 1 minus cos theta divided by 2 into d theta. So integrating, we will get delta w, which will be equal to wr squared into L divided by ei plus wr cube divided by ei and 5 divided by 4 minus 0 plus 0 minus 0. So after solving these two solutions, you will get da by w, which will be equal to wr squared divided by ei L plus r 5 divided by L. So you can try out this sample David beam. We will consider approximate energy methods in the later chapters.